And just a minute, got it. And indeed, including most scientists who use equations all the time, but often don't really understand what those equations mean. Enormous advances were made by Galileo, Descartes, Leibniz, and Newton in understanding the motions of objects in space and time. They struggled towards a deeper understanding of the manifest fact that objects not only stand in spatial relations, but they also have changed those relations, coming closer together, coming farther apart. This means that objects not only have relative positions, but they also have relative velocities, and they change their velocities. They accelerate and decelerate, and they can accelerate or decelerate at different rates. To understand all this more fully, it was necessary to develop the mathematical calculus of variations. And to understand the calculus more fully, it was necessary to develop set theory. And note well, all this mathematical advance resulting in set theory was required in the achievement of an understanding of the physical world. We maintain that this advance in mathematics and the mathematical sciences, what this required was a recognition of the fact that there are in the world not only objects, but also properties of those objects and relations that hold between those objects, and that those properties and relations also have properties and stand in relations to one another. In particular, properties can stand in mathematical relations to one another. Something can be going twice as fast as something else. So, in general, there are properties and properties of properties and relations between relations, and so ad infinitum. In set theory, we grasp these higher order properties and relations by speaking of sets of sets, and sets of sets of sets, and so ad infinitum. For instance, the set of objects that are moving towards us contains objects that share an important relational property, an important relation with us. That physical relationship itself stands in important relationships to other physical relationships. For instance, this property of coming towards me, that relational property, stands in a very important relationship to a very different property that objects share when they're moving away from me. The relationship between the property of approaching us and the property of receding from us is very different from, for instance, the relation that holds between color properties when we notice that red is more similar to orange than it is to yellow. So properties have properties and stand in relations. These properties and relationships can be paired with sets of sets, and that is why set theory is so useful in the mathematical sciences. But it's well to remember that it's useful because there are in the world not only objects, but also properties and relations. Yet philosophers persist in trying to understand the world without ever thinking or speaking about any properties of properties, but only of words and objects. Words and objects. I'm echoing the title of a watershed philosophical work by Klein, Word and Object. We think about concrete individuals that can poke us in the eye or hit us on the head, and we recognize that we can describe these things in language, and we clearly must also recognize the existence not only of objects, but also of the words that describe these objects. We recognize that there are descriptions that seem aptly fitted to the objects we meet. And in science, these descriptions have evolved into complicated equations. Some of these equations express what we think of as the laws of nature. Now, scientists learn to use these equations, these symbolic structures, for practical purposes. But the equations are generally much smarter than the people who use them. Even those who can manipulate equations efficiently seldom fully understand what they really mean. Many think that the symbols in these equations refer to abstract objects, meaning they do refer to something, but that they do not refer to anything physical. Take, for instance, in an equation when you have the little letter I for the imaginary number that's the square root of -1, people assume that that refers to the square root of -1, but that the square root of -1 is not a physical thing at all. And some people, as they put it, think that numbers don't really exist. Hence the symbols used, all the symbols that refer to numbers in the equations for the laws of nature, refer to nothing at all, according to philosophers of this inclination. One such philosopher who thought that the symbols and equations expressing the laws of nature refer to nothing at all was Nelson Goodman. His colleague, W.V. Quine, once made fun of this kind of nominalism in a footnote in which he included a comical rhyme, which I'll recite for you. The unrefined and sluggish mind of Homo javanensis could only treat of things concrete and present to the senses. Given the elitist attitudes rife at the time at Harvard, Goodman might well have seen it as an insult to be compared with Homo javanensis. But he stuck to his guns, insisting that although there may be more things in heaven and earth than he countenanced in his philosophy, he was more concerned to ensure that there were not more things in his philosophy than there are in heaven and earth. Both Quine and Goodman were struggling to understand the equations that are used in formulating laws of nature that involve these advances in the mathematical sciences over the last 500 years, but they're handicapped because they were unwilling to think about or talk about not only words and objects, but also properties and relations and properties of those properties, and so ad infinitum. An equation that purports to express a law of nature contains descriptions of things that may aptly be called states. There's the description, which is the symbolic equation or whatever, but there is also something that this description describes. So, and a state may have further properties, may fit other descriptions, and so on. And so there's a paper that Martin Leckie and I wrote, Leckie and Bigelow, and Leckie wrote another paper in which it's urged that these states can be construed as properties that are instantiated by aggregates of concrete things. Where it is to be stressed that these properties often involve complicated conjunctions and disjunctions of properties and relations that hold among properties and relations and so on. We urge that these relationships can best be articulated using the resources of what is known as a categorical language or a lambda categorical language. In such a language, given any description of a thing, it's possible to construct a name of the property that is thereby ascribed to the thing. Given a description of a thing as being thus and so, imagine the string of symbols being thus and so, and being two things that are distance r apart, and the first one has a mass m1 and the second one has a mass m2. So there's a big description here. That's a big system of symbols. In such a language, given any description, it's possible to construct a name of the property that's being ascribed to the thing with this description. This description ascribes a property, and you can name that property. Given a description of the thing as being thus and so, we construct an expression of the form being a thing that is thus and so. It's often written as lambda x, being a thing x, lambda x, or x with a little hat on top of it, a little circumflex. Two different symbolisms. They're both ways of saying being a thing, call it x, such that X fits the following description, and then you give the description. The full construction, lambda X such that X dot, 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 is called a lambda abstract. And in current semantic theories of these languages, this abstract is taken to refer to a set. But we urge it's better to think of it as referring to a property that's shared by all the members of that set. In lambda categorial languages, abstracts can be recycled recursively in the construction of more and more complicated abstracts. Semantics tracks this recursive process of embedding one lambda abstract in a larger lambda abstract, in a larger lambda abstract, and so on. That's a syntactic nesting of one construction inside another construction that is tracked semantically as referring to sets of sets of sets of sets, and so on. It's all done in set theory. But we suggest that you should really think all the time, remember that these sets are sets of things that share something in common. What they share in common is a property. And it may be a property of a property of a property, and so on. Thus, now what we say is that most laws of nature have this complicated structure like F equals G M1 M2 over R squared. What that really says is anything that fits the following really complicated description. There are two masses. First one's M1, the second one's M2. What does that mean? That means these two have properties, and their relationship to an arbitrarily chosen unit is given by the numbers. M1 and M2 are then represented by numbers that represent a relationship to a unit, so many times more massive than the chosen unit mass, and so on. So there'll be, in a description of a law, there are many, many terms that are referring to quite complicated properties and relations among properties and relations. But it's important to remember, we urge that although the description of a law of nature has all these terms that refer to properties of properties and so on, all these things are grounded out. They terminate, the properties of properties of properties eventually terminate in shared properties of concrete physical things. That's our account of the way that laws of nature are linked to the physical world. An equation that encapsulates the law of nature is the existence of a relationship that holds between one property of a state and another property of that state. In general, most laws anyway, can be expressed in the form of a description of a relationship that can hold. Are we going okay?
Yeah, you've got 10 minutes.
Yep, okay. Between one property of a state that might be called an antecedent property and another property of a state that might be called a consequent property, and our account of the relationship of what these laws state is that one of these laws states that if a system instantiates this property, that necessitates it instantiating some other property. There's a necessitation relation, we say. Now, the explanation of the antecedent and consequent properties is complicated. The relationship between them that we're calling necessitation is also tricky to explain. So the antecedent state necessitates the consequent state is the idea, but that's a natural necessitation. So in our paper, Leckie and Bigelow, we explain that it's a kind of natural necessitation, which means it's not a strict entailment between antecedent and consequent properties unless you add what's oftenly called or thought of as a ceteris paribus clause. So long as things that are going on are all perfectly natural, there's no interference from that, or so long as there's everything that's going on is only going on within a given domain, then you get a necessitation of the consequent property. But that law only holds within a given domain. So the general law, I was going to put this up as a picture, but we haven't got the technology sorted out. Sorry, folks. I can just ask you to visualize it. Lambda x is this little symbol you use for being an x such that it meets this description, the antecedent description. Necessitates being an x such that it meets the consequent. So having this property necessitates having that property, where the first property is a complicated property formed by taking a complicated description and then making a name of the property that's being represented by that description. So to illustrate, just using Newton's law of gravity, the law might be articulated as taking something like the following form. The property of being a system X, that's lambda X, the property of being a system X containing two objects, A and B are both parts of X, and A has mass m and B has mass n, and there's distance r between A and B, necessitates the property of being a system in which there is a force that's acting on A and is equal and opposite to a force that's acting on B, and the ratio of this source on A to a suitable choice of a unit force is proportional to the ratio of m to a unit mass and n to a unit mass, and inversely proportional to the square of the ratio of the distance r between A and B. Now, that's really complicated. F equals g m1 m2 over r squared is shorter, but it's really complicated, and there's no way, unavoidably, when using a lambda categorical language to tease out what the law states, the relevant formula looks complicated. But the basic form is simple. The formula is expressing a law of nature, which is a relationship between two properties that are out there in the world. That's the view we are wanting to defend. So the picture is there's some description of a property being an X such that it meets these fits this antecedent description, necessitates being an X such that it satisfies the concept. That's a relationship between two properties. So our account of laws that we're wanting to defend takes the same general form as a theory that traces to Dredske, Tooley, and Armstrong many decades ago, according to which laws of nature consist in necessitation relations between universals, understanding universals to be properties or relations. Right, so their formula took the really simple mnemonic. The law of nature says N, F, G. Necessitation relation holds between a property F and a property G. Yeah, okay. It's yes, so I will wind up then. So that's the form we want to defend, that laws of nature are describing relationships between properties. This has faced a series of objections, and one of those objections has been, we've noticed, persuasively footnoted and articulated in a recent article in the Australasian Journal of Philosophy by Peter Tan, and we've been puzzling over that. Here's my summary of Tan's objection. I'll move on to Martin next. he's going to talk more about background. But the basic objection is that Tan says many laws of nature are framed in terms of ideal systems of various kinds, frictionless inclined planes, ideal gases containing point-sized molecules that have perfectly elastic collisions, objects traveling in a perfectly straight line because they're acted on by no forces whatsoever, planets traveling in perfect ellipses with the straight line from the planet to the sun, sweeping out equal areas in equal times, and so on. Those, he points out to many examples of laws of nature, which seem to be describing relationships between ideal descriptions of ideal systems of one kind or another. And that seems to involve describing properties, ideal properties that are never to be found in the material world, properties that are uninstantiated. So the law of nature seems to be describing relations among uninstantiated properties. Well, we're not happy with that picture, that laws describe relations among uninstantiated properties. And we're wanting to defend the view that laws of nature just aren't describing uninstantiated properties. They're describing the ways things are actually happening in the actual world. They're describing physical properties and relations. And there's the, we began thinking, I thought a lot about Snell's laws, which Snell's law is the law of refraction, which Newton just described as the rule of refraction. It's also called Descartes' law, I believe, about how light is refracted. And they described this as a law of nature, despite the fact that it was well known, and they discussed at great length the existence of certain crystals, Iceland spar in particular, that polarize light and that don't obey the law. So the law only applies within a certain limited domain. Martin has been thinking more about Galileo and inclined planes. And then Martin and Adrian have been thinking about quantum mechanics. So Martin's going to talk a little bit about Galileo and Newton and the conception of laws, historically speaking, for Galileo and Newton. And then Adrian will talk about the joint paper that he and Martin have been writing about quantum mechanics. And the general drift is what I'm setting up is the aim is to argue that these laws do describe the world. They don't describe some airy-fairy abstract world, Platonic realm outside space and time. They do describe properties that are present in physical situations that are discussed in science. It may be, there's two main ways in which this works. One is it may describe component forces rather than resultant forces. The components are like potentialities that are present, but are being masked because they're overlaid by other interfering factors, which are other potentialities that are also present. So the law is only describing some of the factors. And the other way is that the law may be describing the property that is actually instantiated is one that involves a bit of abstraction. So planets move in approximate ellipses. That's an instantiated property. The property of moving in an approximate ellipse is instantiated by the planets that actually exist. The perfection of ellipses is not required. So I finish.
Take a couple of questions.
Yeah, okay, time for a couple of questions and then I'll move on. I want to leave time for Martin to talk about some quotes from Galileo and Newton. Okay?
Yeah, you take some questions.
Right. So I coordinate this. Sam, I guess.
Yeah, so it's just about this sort of idealization stuff. there might be another way you could go that uses some of the sort of higher order, properties of property stuff that here. So, okay, so you've got, laws being relations between these sort of ideal properties, say, or uninstantiated properties. But you might think that there are going to be similarity relations between the properties that the ideal laws link and the actual properties in the physical world, where those similarity relations are sort of like property of property, like it's when properties have properties in common or something like that. So there's a sort of Tversky style account of similarity where it's about properties held in common. And so, I mean, it depends on whether your worry is about uninstantiated properties or whether the worry is about linking the ideal properties to the physical world. But I think if it's about linking, then similarity could work there and it would be compatible with the rest of the sort of lambda abstraction stuff that you're interested in.
Yeah, great, good. Yes, I think that's right. The one way to say so a thing's got a property. One way to say what that property is like is by saying it's like some other property that's easier to think about. So you can't say exactly what path the Mars is traveling. It's very complicated because it's got perturbations from Neptune and Jupiter and so on. But it's pretty similar to an ellipse. So that's one way of describing the property that is instantiated. Yes. That's right.
Yeah, and then similarity itself can be about property sharing, but like higher order property sharing.
Yes, higher order property sharing. Yes, exactly. Well, I didn't have time to get onto this fully, but Peter Tan's worry is that often the idealizations seem to not only require us to think about uninstantiated properties, but impossible properties. In some sense of strong sense of impossible. So if you're thinking of an ideal gas law, you're thinking of the molecules are treated as points. But if the full mass of that molecule were compressed to a point, it would be a black hole. And it wouldn't do the things it's supposed to do according to the ideal gas law. They wouldn't be perfectly elastic collisions between them, right? So that's a further complication that we're wrestling with. But I'm hoping that the thing you sketch as a strategy, there's all sorts of resources available there.
Just quickly, I mean, possible things can be similar to impossible things.
That's right.
It seems like it should generalize that in that direction too.
Yeah, impossible things like being round and square as a conjunctive property have two parts that are not impossible as well. So often I think that these aversions that you sometimes have towards impossibility, point particles and so on, is really all you require for the law is very small, and the smaller they are, the more closely it approximates this equation. Okay, thanks. Yeah, thanks for that. Other questions? I'm having to look at both the big screen and the little screen at the moment. Or should we move on to the next presentation? Yep. Okay, on you go. Mark. So I give you the speaker here.
And Michelle, set up that. All right, and what? Getting set up. Don't do that. Okay, and so what is that? Oh no, so I'm using this here. So can people hear me all right? Yep. All right. So Yeah, I'm Martin Leckie. I'm not Adrian Flitney, is that?
That's right.
This is showing Adrian Flitney, but yeah, I'm a colleague of, well, associate at the University of Melbourne and colleague of John and also of Adrian. We work together on metaphysics in the case of John and quantum theory in the case of Adrian. So I'm going to be talking about applying this, or talking about our theory of laws, but in taking up this challenge of ideal laws from Peter Tan, but talking about it in the context of classical physics and using Galileo's law of free fall as an example, because Galileo is, this law is often referred to when we're thinking of idealizations. Yeah, so this is my talk. You know, because there is no such thing as frictionless inclined planes that sometimes talked about in relation to that law. So I thought I'd go back and look at what Galileo actually said to see if it's compatible with the kind of things we want to say. So anyway, so this is the paper we published in 1995. It expressed laws as a kind of relation between universals, between properties. And there's a relation that involves a natural necessity. Missing one, this one. Go back to the other ones. This was our formalism that John explained. So lambda x or x hat being an x such that being a system such that the system is in a certain situation, like near the surface of the Earth, moderate sized body, and everything is natural conditions, entails that being something such that that relationship will hold, like the if you drop it from stationary, the law of free fall of Galileo says that it will fall, velocity will increase with the acceleration, g, or v equals gt, or the distance is proportional to the time squared. So, is the way he put it. Now, Galileo, yeah, so I'll just, before I get on to idealization, I'll just say a bit more about the example. Now, just to actually measure distance versus time, it's too difficult. We're dropping things vertically, so you put it on an inclined plane. It slows things down. But the velocity actually independent that it gets up to from a certain drop is independent of the distance traveled, because horizontally it doesn't slow down at all. It's frictionless or speed up at all. So it's just a drop that increases the speed. So it spreads over a much longer time to get to that same speed. So you can measure, he did it with a water clock, measuring the time taken and found to be proportional to the square of the time. Oh, sorry, the distance, square of it goes with the square of the time. But obviously there'll be some deviation from that due to friction and maybe air resistance, only friction. So he set up, he said he set up a hard surface and so on, a hard ball to do as best he could. But he said, we've got to idealise away from this situation to find out the actual drop due to gravity, which he's trying to do. So, yeah, Peter Tan says that things like this, laws really are only about what happens with ideal frictionless surfaces and so on. That's what the laws are about. Whereas we were saying that, we said that, no, that's not true. What they're about is a component of the motion due to gravity is what the law is trying to do. And sure, there'll be a deviation from that due to other factors, such as friction, but the law will correctly describe the component due to gravity. So you can break up the motion into different components and break up acceleration into different components and the forces. So there'll be a component force due to the component acceleration due to the acceleration and the resistance. Anyway, let's have a look what now, how do we get the, I want to be able to see the whole thing. Oh, yeah. You can minimize it.
Yeah, no, it's fine.
Oh, that didn't do it.
It's done. Oh, I see. It's not done thing.
So, oh yeah, so, oh no, we didn't have, it wasn't the right version. We go back one.
We can see your whole screen.
We can?
Yep.
Okay. So there's three, in a paper by McMullen, he breaks up Galilean idealization into three different kinds. Mathematical idealization, yeah. Construct idealization and causal idealization. So we'll just go through that. So when you apply mathematics to a situation, you leave some of the things behind, but it's hope that you get the essentials of the situation. And certainly for Galileo, this wasn't really an idealization at all, because he says that nature was written in the language of mathematics. So it's nature is a grand book that's written in the language of mathematics. And its characters are triangles, circles, and other geometrical figures, without which it's humanly impossible to understand a single word of it. So he thinks that it's not really an idealization at all, really, because although the mathematical form that we come up with will be, but nature is actually mathematical. So it'll get, yeah, maybe idealize, maybe yeah, actually what he says here will explain it more. So there was he puts in the words of Simplicio, which is used for sort of Aristotelian objectors, who says, objecting about using maths to capture what's happening, because things aren't perfect spheres and they don't touch at a single point on the plane and so on. So he's objecting to that maths won't actually fit. And Salviati, who's Galileo's spokesperson in the dialogue, responds, just like a businessman has to allow for boxing and packaging, reading the real from observed weights in his wares, so the geometrical philosopher has to, when he wants to recognize that in concrete, the effects which he has proven in the abstract, must allow for the impediments of matter. If he's able to do so, I assure you that things are no less in agreement than our arithmetical computations. The errors lie then not in the abstractness or concreteness, not in geometry or physics as such, but in a calculator who does not know how to keep proper accounts. So even if things aren't a perfect sphere, there'll be some shape. Even though the ball isn't a perfect sphere, it'll be some shape. So geometry will still apply to it, even though it's a concrete thing. So that's, I think that's what he's saying there. Now, I can say more about mathematical idealization later, maybe in question time, exactly what his status of mathematics was for Galileo, but he thought maths was something independent of us, perhaps ideas in the mind of God. So now I'll go on to construct idealization. What happened then?
Yeah.
Can you hear me still?
Yep, we can still hear you.
Because I'm in the same room.
So would you like me to continue
Yeah,
sharing?
so maybe Jacinta, can you just do the continuing?
Yeah, just give me one.
Actually, I'm a little bit behind time, so I need some water. Can you,
So I think it's,
we're up to
I think it's.
Yeah, so
Just
just
one-
move on to the next slide.
next slide, yeah. Yeah, so construct idealization is idealization in the representation of this situation. Maybe where things are just not quite if things aren't really perpendicular to the Earth, the weight because of the curvature of the Earth and so on. So there'll be approximations in that sense. Maybe I won't go into that so much because that's not the most important one. And he had various ways of answering this. This is an early answer. He just said he's following an example of Archimedes, who made the same kind of assumptions. And there's not a very good answer at the end here. He said, and he did so perhaps to show that he was so far ahead of the others, that he could draw true conclusions even from false assumptions. So this is an early work, de motu, which wasn't published. But later on, he goes on to make quantitative estimates and arguments that it wouldn't make very little difference. The balance, for example, is spread over such a short time direction. It wouldn't make any difference to vertical curvature of the Earth because it's actually the force is directed towards the center of the Earth. So I'll move on to, the next one, slide. Causal idealization, which I think this is the most important kind of idealization that Galileo was involved with, where you're trying to isolate causal factors, and always got practice there, or reducing or otherwise compensating for interfering complicated factors. So in this case, law of free fall, what he wanted to discover was the downward tendency the body has from its own heaviness in the absence of all other causes. Can you see all of that? We can't see quite.
Yeah, yeah.
They can.
Yeah.
All right. All right, next page. So now he had different ways of talking about this kind of idealization. I mean, this is the kind of idealization that's central in modern science. We try and isolate certain factors that we're trying to look at through reducing other interference or otherwise compensating for it. So what he says here is, yeah, this way he says, this does sound a bit like the law doesn't apply to the world. Our demonstrations, as we have said above, must be understood as bodies feel free from all external resistance. But since it is perhaps impossible to find such bodies in the realm of matter, one who performs an experiment on the subject would not be surprised if the experiment fails. So it's also, that was from Demoto as well. And next slide, sorry. So again, he says, this proof of inverse square law of fall is to be understood on the assumption that there's no accidental resistance occasioned by roughness of the moving body or of the inclined plane or by the shape of the body. We must assume that the plane is, so to speak, incorporeal, or at least that it's very carefully smooth and perfectly hard. So as the body exerts its pressure on the plane, it may not cause a bending of the plane and somehow come to rest on it as in a trap. So you see, so in some ways, yeah, it sounds like he's talking about incorporeal in that first part. So it's unreal things. But on the other hand, he's saying, well, at least let's try and approximate that by making it perfectly smooth and hard, so on, to minimize the factors. So this is, now this is later on, this is his more sophisticated kind of response that we think is more in line with this idea of isolating this, what would happen. I mean, isolating the factor that's due to gravity alone. And this is his most sophisticated answer to that problem, which came in dialogue of the two new sciences. So, about 1630, I think it was. So we're trying to investigate what would happen to movables, very diverse in weight, in a medium of quite devoid of resistance. The whole difference of speed existing between them has to be referred to the inequality alone. Hence, just one space entirely void of air, right? And every other body, however thin and yielding, would be, yes, right, would be suitable for showing us sensibly what we seek. So in other words, a void. Since we lack such a space, let us instead observe what happens in the thinnest and least resistant media, comparing this with what happens in others less thin and more resistant. So for example, he would have tried air and water. If we find, in fact, that movables of different weight differ less and less in speed as they are situated in more and more yielding media. So he's talking about the law of free fall here, rather than on a plane. And that finally, despite extreme difference of weight, their diversity of speed in the most tenuous medium of all, though not a void, is found to be very small and almost unobservable. And it seems to me that we may believe, by a highly probable guess, that in the void, all speeds would be entirely equal. So this is his arguing that the law of free fall is independent of the weight of the body and the composition and so on, in opposition to Aristotle, who thought that heavier bodies should fall faster. So this, I think, points to the idea that you can get empirical evidence that what would happen in the ideal, in the case of a void, and so isolate the contribution that is due to gravity alone, acceleration due to gravity alone, and the force due to gravity alone. And so you can get evidence for the existence of those factors. In contradiction to others who say that laws are only about idealizations or unreal situations, we're saying these things do exist. There is a component of the force due to gravity in the actual situation, but it's got other factors as well, like the air resistance. So I'll just quickly say something about other accounts of what Galilean idealization is. There's a well-known account given by Weisberg in 3 Kinds of Idealization, where he says what idealization is, which I think is a bit misleading what he says. I seem to have missed a bit out there. Galilean idealization is a practice of introducing distortions into theories with the goal of simplifying theories, in order to make them computationally tractable. I can leave out that fragment of a sentence. And then the next paragraph, Galilean idealization is justified pragmatically. Since the justification is pragmatic and tied to tractability, advances in computational power and mathematical techniques should lead the Galilean idealizer to de-idealize, removing distortion and adding back detail to their theories. So, but what we saw in what Galileo has just said, he's really trying to go the other way. Rather than adding detail in, he's trying to remove this detail to get to isolate the real contribution from gravity. So this is a misleading account of what Galilean idealization refers to. Sure, once you've got that, once you've isolated and understood the contribution from gravity, then you can add the other things back in to give a more of an account of what you actually see. But he thinks that getting to the real hub of the matter, what's that?
Slide.
Oh, not yet. Maybe we can go back one. I think I'm not going to talk about the last slide. Have you got Weisberg on Galilean idealization? Forward. Go forward. One more. No. Maybe you got a different version.
That's all that's in the slide you sent me.
Okay. Well, I've got a different version here. Anyway, that's if you heard what I said anyway, there's just a different account of idealization that I think is misleading. So maybe just relating it back to just briefly relating it back to our theory. Yeah, we think the relations that is picked out between properties picks out something that mightn't be instantiated in any case, that particular case, but it identifies real properties in the world, like the component of the force due to gravity. And Galilean idealization is actually aimed at trying to discover those factors. So maybe I'll just leave it there for now, and I can take any questions. Yeah. I can't see her name, but on my screen.
That's a clapping hand, not a raised hand.
Oh, right. Sorry. Sam.
Yeah, I just wanted to suggest another account of idealization that might be helpful. Michael Strevens has an account of idealizations where he says that what's happening in an idealization is it's telling you that some aspect of the physical system doesn't make a difference to whatever it is that you're trying to explain or understand. So, for instance, when you have a frictionless plane in your set up in your model, whatever it is that you're using to do some explanation, his thought is that that's telling you that friction is sort of not really relevant to what it is that you're trying to understand. And I wondered if that would actually be quite helpful for you, because if you're worried about these sorts of uninstantiated properties or these relations between ideal things, it could be that rather than idealization sort of telling you that something's not happening, it's really giving you information about what is happening, namely that certain things are not difference makers or not relevant. And so certain properties aren't being linked by relations of, like, by necessitation relations could be what the idealization is telling you. And that seems like perfectly compatible with the way that you'd be thinking about it. Anyway, I just wanted to offer that as an alternative way of thinking about idealizations. Rather than giving false information, they give you true information about difference making.
Yeah, well, certainly Galileo was saying that what he was trying to get was the essential aspect of what's going on.
Yeah, that's right.
And, you know, going on Aristotle's idea of essential properties, whereas he called these accidents, the other things, the friction and the air resistance, that he wasn't so interested in, because he was.
So Sam's suggestion is very much along those lines.
It is along those lines, and but our account can. I mean, I think the law, as we applied it, we said that well, there's two ways you can go. You can either say that the relation between say distance and time is approximately true, or you can say it's exactly true for the gravitational component. And I think the necessitation would still apply in both of those cases, because it's essential that the gravity applies, and in all real law-like situations, it's also air resistance and so on are there as well. But yeah, they're just not the part that you're interested in, or Anyway, thanks for that. Well, any other questions? Yeah. Okay. Can't see very well.
I mean, I have another question, but I don't want to take up too much time if you want to move on.
Yep.
So in some of the stuff in idealizations, I think Weisberg, there's a bit of this in Weisberg, and allegedly some of this in Galileo. This idea of a Galilean idealization is that eventually you want to get rid of it, right? So like an idealization is something that's a sort of like poor description of something that if only we were better, we would be able to give an accurate description of. And the sort of goal of science is to remove the idealizations and make them fully concrete and not ideal at all. And when you were sort of disagreeing with Weisberg, I wasn't sure if this was an aspect of the way that you were thinking about idealizations, or whether you were thinking that idealizations are sort of there to stay and sort of need to be dealt with that way, or whether you can sort of eliminate them eventually.
Well, I think it's a slightly complicated situation, because the way I was describing it, I thought the way he put it was misleading, because what Galileo wanted to do in idealizing was to find the essential part, for him was the essential part, the contribution from gravity, from the weight to the motion. And therefore you're trying to subtract away the complication. But once you've done that, and you want to understand the concrete situation, you can put what you've learnt from the contribution due to gravity and add in back in the other factors like air resistance and friction. So it just depends what your aim is. If your aim is to describe the full situation, then yeah, sure, you can do that, and that would be a progress in that aim. But what Galileo was more interested in was finding contribution from gravity. He sort of could see, we knew how things behaved without them more, but yeah, he was interested in that part. So idealization goes the other way, where you try and estimate what would happen without gravity, with those techniques he talked about. So can you see, yeah, how I think it's misleading the way that Weisberg talked about it, although that's certainly part of what you can do with this, what Galileo is doing, is add back in those complicating factors.
Thanks.
All right. Well, we can go on to Adrian.
All right, Jacinta, I will use your copy because I've lost my internet connection. So I'll just move a bit closer so I can be. Sorry about the noise. Set microphone. Right, so it's good there. Okay. Well, I'm Adrian Flitney, and you've just heard from my colleague Martin, friend and colleague. So I'm sort of loosely connected with RMIT, and we've been working on this project, which is a physical collapse model in quantum mechanics based around discrete physics. And it's, as we'll see, it sort of necessitates, or certainly allows, and I think necessitates, a realist view of what the wave function is. So I'm going to start, next slide. Okay, so I'll start talking a little bit about what we understand by realism in classical physics. So I'm not going to go into a lot of detail there. I just want to set the scene, and then about what the view of reality in quantum mechanics. And because, well, you know, quantum mechanics is a bit fuzzy, and certainly debate around whether the wave function itself is a real thing or just is a tool for calculation. Well, that's been going on ever since there was a wave function. So then I'll do a little diversion into discrete physics, and that will lead us onto this model of spontaneous collapse of the wave function, and then we'll see how that leads to a realist view of the wave function. Okay, so next slide. So these are just some quotes about realism and quantum mechanics. So Einstein, of course, was well known as a realist. It is a basis for physics that one assumes a real world existing independently from any act of perception. But this we do not know. Nielsen and Chung, in their great tome, Quantum Computation and Quantum Information, stating the sort of orthodox view in quantum mechanics that says, well, Bell's inequality points to the conclusion that either or both of locality or realism must be dropped from our worldview. And Fine goes a bit further and just says, well, realism is dead. Basically, Bohr won over Einstein. So let's go on to the next slide. So in classical physics, we have come to a view. There are several features of reality. One is that it's atomistic in nature. We can keep dividing things up until we get to some component parts of the system, and these are separate individual parts, and then they interact by means of forces. And at every instant in time, all physical quantities pertaining to a system have definitive values. Next slide. And if a system does possess a certain property, then it does so independently of how we choose to measure that property. And so if one is able to determine all the properties of all the atomic objects in space and time, then one has a complete description of the world. Next slide. So this is just a little bit of summary. You know, I am a physicist and not a philosopher, so people may object to my summarizing classical realism, but this is just from my readings. So yep, we have independence of physical reality from the observer. We can form objective knowledge of an object by creating a representation of that object. And it possesses all of its properties in and of itself. And then we have this correspondence between the way the world actually is and the way we observe the world to be. Next slide. So orthodox quantum mechanics, we have to throw out some of these ideas of classical realism. So I think nearly everyone, well, certainly everyone working in the field of quantum mechanics will sort of, nearly everyone will accept that. So firstly, quantum mechanics violates the idea of separability. So this is what we get when we have an entangled system. So, I mean, I don't know everyone's background, but we could have, for example, a pair of electrons with opposite spins. And what we know about the pair is that their total spin is 0. And yet we can't infer from that the spins of the individual electrons. All we know is once I've measured one, I know what the other one is. But until I've taken that measurement, I actually have no idea what the spin is. I mean, it's spin half, I don't know the direction of the spin. So the maximal determination of the whole system doesn't allow us to acquire all the information about the component parts. And the other thing we can say is, well, again, this is the orthodox view, we cannot assign definitive sharp values to all quantum mechanical observables. Next slide. So properties are contextual. So this means that it depends upon how I choose to measure the spin of that electron, for example, as to what answer I'll get. So I choose a particular basis about which to measure the spin, and then I'll find spin up or spin down around that basis. I choose another basis, and I'll find a different value. So the properties of a quantum object are not well defined outside of the measurement interaction. So we know the results of measurement, but we're a bit fuzzy about what's happening in the rest of the time. And properties are non-local. So again, it's very hard to argue with, certainly non-local in physical space. If I take an entangled system and I separate it, then the properties of those individual particles are now spread out over the whole system. Next slide. So we have this world according to quantum mechanics. We have a highly entangled whole. And if we are true to quantum mechanics, because there's no such thing as a system that has no interactions with its environment, in fact, we really have to write down a single wave function for the whole universe. So, yeah, as I'll go on to say, we do write down wave functions of smaller systems, single particles, entangled pairs of particles in quantum mechanics, but essentially they're always approximations that we get by neglecting the interactions with the environment. We can agree that there's only one external reality, but our description of it will depend upon our point of view. So in other words, what measuring apparatus we set up. So there's no such thing as this sort of universal or God's eye viewpoint, a view from nowhere, as Nagel says. And most people working in quantum physics will take the wave function as being merely a computational tool for the predictions of the results of experiments and not as a real thing in and of itself. Okay, next slide. Now, the measurement problem, well, anyone who has more than a passing interest in quantum mechanics will have come across the measurement problem, and there are as many descriptions of this as there are quantum physicists, but I'm going with McQueen's description of the measurement problem as a trilemma. So we have these three statements. We've got the wave function being a complete description of the physical properties of a system. We have the wave function always evolving according to the Schrodinger equation, and a measurement always giving rise to a single determinate outcome. Now, one of those three, well, let's just say those three are inconsistent, because we know we have systems that are superpositions, and if the superposition evolves according to the Schrodinger equation, it remains a superposition, but when I take the measurement, I get a single determinate outcome. So that's the basic issue with the measurement problem. All right, so now this little diversion into discrete physics. So firstly, I should say, well, whenever we real numbers, well, they may or may not exist in nature. They may just be idealizations. So I'm not going to go one way or the other with that, but what I'm going to do is say, let us see what happens if we actually assume that everything is discrete and that there are no such thing basically as real numbers in nature, and see where that leads us. So firstly, we have to have the state of a system, all values, all properties are discrete valued, and there are a finite number of properties. And we're going to discretize physics with, not with the aim, as some people have done, such as Gerald Tufte, of approximating a continuous reality. We're going to say, this is actually what reality is like, and then we're going to explore the consequences of that. And we will not assume that this underlying discrete physics is classical, local, linear, and Stephen Wolfram assumes that it's reversible. He has a cellular automata, a method of discretizing reality, so we're not going to assume that either. Next slide. So we have to be clear, when we say we're going to discretize everything, we have to discretize the wave function. So normally we write out these wave functions as continuous functions, exponentials, polynomials, sines and cosines. But the way we're going to choose to discretize the wave function is saying it's a magnitude, that's the magnitude f, times a phase factor e to the I theta, and both f and theta will be integer multiples of some base values. So f0 being the base magnitude and theta 0 being the base phase angle. And of course, these natural numbers n, f, and n theta are functions of here, the positions. So here I've written down a wave function for, I should say, of n particles with positions x1 to xn. So, and of course time there. So the nf and n theta will be functions of those positions and of time. Next slide. So one thing, once we've discretized the wave function, there is a minimum magnitude that's representable in this physics. That's the f0. So as the wave function spreads out in time, the tails of the wave function will drop below F0 and then they'll actually be 0. So a wave function doesn't extend off to infinity. It is finite in extent. And this finiteness is in the 3 n-dimensional configuration space. If I have an n particle system, then my configuration space has 3 n dimensions. So this is, if you like, so it's the space that wave function is living in. And I'm going to divide that 3 n-dimensional configuration space into unit cells. And here I'm allowing the cell size to depend upon the particles. So if I've got n particles here, the cell size for the first particle is A1 cubed. I'm assuming some discretized space. Now this is discretized space in configuration space, but we would assume that physical space is also discretized. And so on. So AK here is a characteristic length for the kth particle, and this product A1 cubed ... up to AN cubed is a volume in this 3 n-dimensional configuration space of a unit cell. Next slide. And then we can define the relative volume occupied by this wave function. So we take the volume V here, which is this 3 n-dimensional volume in configuration space, for which the wave function is non-zero, remembering that the wave function is dropping to 0 as it spreads, so it's finite in extent. And we simply divide that by the size of a unit cell. So we are saying this relative volume is in fact just a number. It's the number of cells for which the wave function in configuration space is non-zero. And if we were to take into account spin, we would have to multiply the spatial wave function by 2 to the power n components. Now, we're not going to deal with spin, and you know, we're only dealing with here non-relativistic quantum mechanics, but we could extend the theory to spin once we get the rest of the theory under control. All right, next slide. So in orthodox quantum mechanics, as I've mentioned, the wave function of a single particle or a small group of particles is always just an approximation. But in our model, we're going to treat these wave functions as real independent entities in and of themselves. So we can write down a wave function of a single particle, perhaps, or of a few particles. And whenever we have a system of, say, n particles, which is strongly interacting, and we're going to be a little bit vague about what we mean by strongly interacting, then we can write down a wave function for those n particles, and that wave function will be a real existing object. But it's a real existing object in this configuration space. The next slide. And the wave function, well, over time, it spreads and it's occupying a larger volume. And what we're going to assume is that when the wave function reaches some critical relative volume, that it will collapse, or it could split into 2 or more wave functions. Now, I should say that these wave functions don't preclude interactions between wave functions, but we're assuming that this has to be handled somewhat differently, the sort of weaker interaction between wave functions than within the wave function. So this collapse, when it happens, is, you know, I'm missing out the mathematical details here, I should say. So the collapse, when it happens, will be by multiplying the wave function by Gaussian in the position of one of the particles. And so what we're doing is then concentrating the position of that particle around a certain location. And because we've got a system here of n particles that are strongly interacting, we assume that that will localize the remaining particles in the wave function as well.
That's RGRW directly. It's not quite the same.
Well, it's similar to, yeah, okay. So not quite the same as Martin points out. So I shouldn't say in the same way. We're doing it in a similar way to Girardi, Rimini and Weber. So they came up with this physical collapse model in 1986, and we're using a similar mechanism, but it's sort of analogous anyway. Next slide.
So you're going to say what's motivating the collapse?
Yes. So as Martin reminds me, I should point out what's motivating the collapse. So as this wave function spreads, as we already mentioned, that there's a minimum magnitude representable in this discrete physics. So if it spreads over too large a volume, well, either one of two things would happen. We'd either the magnitude of the wave function would drop below our minimum magnitude everywhere, and then our system has just ceased to exist. Or we could say, all right, well, as it spreads, we're normalizing it. So therefore the magnitude's not dropping, but our wave function will then become disjointed. There'll be regions in which the magnitudes drop to 0. And so we'll have these disjointed regions of configuration space in which the wave function is non-zero. So the idea in this model is Girardi, Rimini and Weber said, all right, we'll have this collapse happening just stochastically by chance at some rate. And this was hypothesized in order to solve the measurement problem. But in our model, we're saying, well, in fact, it's the discrete physics that is motivating us to say, well, if we have a discrete physics, we really need the wave function to collapse to remain compact. And so we're taking any n-particle system with strongly interacting particles, I say relatively strongly, okay, will be represented by a single wave function. And if each particle is spread over some volume V, then the relative volume of the whole wave function will be proportional to this V to the power n. So this relative volume is scaling exponentially with the number of particles. And so that's going to be quite important. Next slide. So because the relative volume is scaling with n, wave functions with a large number of particles will reach the critical volume very quickly and thereby collapse and thereby localizing in space. And wave functions of one or a few particles can take a long time to reach the critical volume and therefore collapse infrequently. So by adjusting what the critical volume is, we're hoping to say, all right, we can allow, say, for example, entangled systems. I think the record now for quantum teleportation, it's been done between Earth and a satellite, around 1,400 kilometers. So we have to allow a system of two particles to spread at least that much. While at the same time, you know, physical objects like chairs and tennis balls and so on, they're going to collapse virtually instantaneously. And so they'll be well-defined locations in space. Next slide. So these collapses are happening whether we're taking measurements or not, but supposing, so of course, if I then take a measurement on a macroscopic system, there is no mystery as to why it's not in a superposition, because it wasn't in a superposition. It's collapsed already because it reached its critical volume. In fact, it'll be collapsing, you know, just all the time. If I take a measurement on some microscopic system, well, in order to get some readout on a dial or some pointer position, I have to entangle my system with some macroscopic measuring apparatus. And by doing so, my system will now have a large number of particles, and therefore I collapse and localize in space. And when we localize, if I'm thinking about, you know, a pointer position here or here, as soon as I localize it, I'm basically destroying the possibility of the superposition. That's the hope. So again, it's then no mystery as to why my measuring apparatus only indicates a single value and not a superposition. Next slide. Okay, so I'll wrap up with this idea of the realist view of the wave function. So in our model, we have these wave functions, and we're treating them as real evolving objects that really collapse. We're not looking at the wave function merely as in orthodox quantum mechanics here, we've got the modular squared of the wave function, just as a probability density for the system being located in a certain region of space. But in our model, we're going to take wave functions as representing real objects inhabiting configuration space. And this integral of the mod squared of the wave function, if I integrate over all the spatial variables apart from the position of particle K, then this can be interpreted realistically either as the density of particle K in position space. Once I've integrated out all the other positions, now I'm just in the position of particle xk. And it's the projection from configuration space into position space of this wave function, or into the position space of particle K. And we'll go to the last slide. So I'm having a little appeal to authority here, and going to Max Born says, I personally like to regard a probability wave, even in 3-dimensional space, as a real thing, certainly as more than a tool for mathematical calculations, for it has the character of an invariant of observation. Okay, so that's all I have to say. I will say that we can use observations of entanglement. We can use observations of cosmic microwave background, for example, to try and constrain the parameters of this theory, as has been done with other collapse theories. So this is more than just an interpretation of quantum mechanics. It actually has different physical consequences. Obviously, we need them to be small enough so that we haven't yet observed them. All right. I'll take some questions now. I can't see everyone. I see Samuel.
I just wanted to see if I understood the way that the collapse works. So is it a sort of like one more chocolate mint type view where, you know, you've got a certain number of particles and then you just add this one more particle and the whole thing collapses? And, or is it the case that the sort of the number of particles needed to collapse might depend on other factors, like the nature of the system or something like that?
Well, we're leaving open the possibility of this unit cell size being dependent upon the particle. So it may depend upon the particle. But yeah, so the system will collapse even if we don't add extra particles to it, because it is expanding in space. Well, I hesitate to say as time evolves after the talks this morning, but certainly with time, it's expanding. But yes, but also, as you say, if I entangle it, yes, then that one more chocolate mint might be enough just to tip it over and cause it to collapse when it reaches this critical volume. And we at this stage of the theory, we're sort of taking this critical volume to be a precise value. But the cell size might depend upon the types of particles.
I see. So collapse is about the volume of the wave function rather than the number per se, but
Yes.
Number just works as a kind of proxy for volume, so that when you add more things, you increase the volume of the wave function. That's why it collapses.
Yep,
so that's
yep.
why when it's spreading can collapse it as well as just adding more stuff.
That's right. So it's in the configuration space. So of course, when I add more particle, I'm actually adding
Another dimension.
well, I'm adding 3 more dimensions to configuration space. So therefore, I'm adding a large amount of extra volume. But even a single particle will eventually spread and reach the critical volume and collapse.
So
I
it's
see.
not one more mint, it's more like the balloon bursting when it gets below 1 quantum in some of the units. Isn't that right?
Where it's threatening to provide.
Where it's
Yeah,
threatening to
well,
get-
that,
where
yes, yes.
it's
So,
threatening-
so
it's
where,
threatening to spread, so as one photon spreads out, its strength in over the surface that it's spreading gets thinner and thinner and thinner. And it can't be below 1 quantum, so if it's threatening to become physically unrealizable because it's less than a quantum, then it has to burst and collapse.
yeah, so the quantum here is this minimum magnitude representable in the theory.
Does that help?
Yeah. I think I was thinking of it in terms of number of things rather than the sort of like volume of space,
Yeah,
for want of a better term.
It's sort of volume in this configuration space. So the extra particle, of course, adds a lot more volume.
Got it.
But
Yeah,
it will
yeah.
reach that volume anyway.
Yeah, cool. Thanks.
Patrick.
Yes, I thought I'd maybe add a question on that point because so I mean I can sort of see the intuition of it when you've got one particle that it can only spread so far in its own kind of configuration space before you're starting to run up against the kind of limits of quantized kind of, you know, magnitude of the wave function. But as you just mentioned, of course, if you add more particles that are entangled to the system, there's kind of more volume, but there's also more configuration space that you're adding. And so like, it's not like I guess it's less intuitively obvious to me as to like why that brings the whole system closer to being like near that lower boundary where now it's going to have to collapse because you're running close to the limit of you know, of your quantized kind of magnitude of the wave. So I guess the question is if that's how measurement works, if adding on more particles means that you're going to run up to the limit and a collapse is going to happen. It feels like there's something missing for me that I haven't understood about why adding more particles, which both means that there's kind of more volume, but there's also more configuration space in which that volume extends. Why that would make you closer to collapse?
But yes, because when you're adding another particle, you're putting up the volume, total volume. So the amount that can go into each cell will reduce.
Yeah.
So remember, it's a dimensionless number in the number of cells that are on zero. So it's going to be more thinly spread, much more thinly spread.
So it's being spread in configuration space in this 3-dimensional space. And,
yeah.
And this critical volume is simply a number of cells in that space that are where the wave function is non-zero.
So this one photon, you've added another thing to the system. This one photon has to have some value in all those extra cells.
That's right.
It'll have to be a pretty small number to be non-zero in all those cells. If it's too small, it's below a quantum. It's not physically real in a discrete physics.
So we're taking...
So it has to collapse.
So adding another particle doesn't have more volume. It spreads the volume. Right?
Yeah, it's adding volume in configuration space, but it's just, we're saying, therefore the wave function is now occupying a much larger number of cells. And we still have the same minimum magnitude. We're not having a minimum magnitude per particle, it's a minimum magnitude for the wave function in this model.
Yeah. I'll have to think about it a bit more. I feel like I don't quite know what my own concern is.
Yeah, look,
but it's very interesting.
I deliberately didn't put much maths in there, so
Yeah. No,
there's
it's
a lot
okay.
more to it than that. Oh yeah, yeah.
No, go on.
No, I was going to say, I mean, if you're interested, there's actually, if we can have the, if Jacinta, yeah, if we can have that presentation back, there's one more slide with some references on it, just at the very end. Anyway, so yep, so Martin's thesis is accessible on the archive, and an earlier paper And we're in the process of finalising, in inverted commas, hopefully any day now, a paper which will go up on the archive and hopefully make some of this somewhat clearer. Yeah, so these are the 2 papers up on the archive already, and Lecky and Flitney will be up there. Well, yeah, we hopefully this year. I think we said that last year too, but just ignore that.
So in that last one, we're doing some of the calculations, constraints on the values of those parameters, and showing where the predictions.
Sorry, Martin, could you put the microphone?
Oh, sorry.
So I can hear you.
Oh, we're just in that last paper that we've already done the quantitative stuff. We've worked out constraints on the values based on the microwave background radiation, what effect it has on the spectrum, and on observing distant stars. The size of the star will slightly increase because
The size of the image, yeah.
size of the image, sorry, the image will increase because each time the wave function collapses, it localizes in space, so it delocalizes in volume, in momentum, and frequency. And so the thing will be a little bit fuzzier than it should be. So we've put constraints on the values using quantitative constraints. So we know where to look for to confirm the theory. That would be ideal.
Yeah, so one,
Yeah, I'll go back.
oh, it's here, isn't it? Yes. One thing with all spontaneous collapse theories is that when the wave function collapses, when you localize it in space, you're decreasing your delta x, if you like, and then Heisenberg's uncertainty principle means, okay, we're increasing delta p, and thereby we actually have non-conservation of energy. And so people have been looking for evidence of spontaneous collapse theories by looking for anomalous thermal noise and things like that. And in our case, I didn't mention, in fact, GRW model, at least recent models, don't have collapse for photons, but we simply say, well, it's all wave functions, so photons are included. So that thereby the image of a star is going to be a bit fuzzier because of the non-conservation of the transverse momentum of that photon as it's going towards our detector. And the cosmic microwave background, because of this non-conservation of energy, the spectrum is going to change slightly. Samuel.
I'm just interested in the sort of projection from 3N configuration space into physical space and exactly how you're thinking about this. So I've got 2 questions. One of them is, I think you said that you think of physical space itself as discrete, which strikes me as different to some of the other wave function realist views out there, where I think they just project into a sort of continuous physical space rather than into a discrete physical space. So I was sort of curious as to why you wanted a discrete physical space and what that would look like. But then also a sort of metaphysical question about the projection itself. Do you think of 3N configuration space as, maybe this is too metaphysical a question, but as like the fundamental arena of reality, and the physical space are kind of like illusory projection? Like, what is it? What is this projection word, and what does it actually mean metaphysically, or is it just sort of a black box in the theory?
Yeah, I think I'll give that one to Martin. He's more into metaphysics than I am.
So,
I want to hear what you think.
yeah, well, he wrote Adrian 6 too.
Yeah.
So, yeah, this was one of the chapters in my thesis about. In some ways, at the microscopic level, the configuration space will be the more fundamental in some sense. I mean, for one thing, look, causality is local in that space. because the wave function only affects those things right beside it, well, most of the time, except for when you get collapses. So that in for macroscopic things, causation is local in three-dimensional space. So these are things they share, but in different realms. So in some sense, I do want to say that configuration space takes on the status that ordinary space has at the macroscopic level, or for ordinary objects. Yeah, so I have this property view of all spaces. So I think they're all spaces of properties, so that they all have equal existence in that sense. Yeah, I took what's called a property view of space in my thesis. But because of their different relations to causation, they'll have different relations to our perception, for example. So we'll perceive things that are, well, it's evolutionary advantageous for us to perceive things that are close to us or that affect us. And so we can see them in ordinary space. Whereas microscopic level, configuration space will have that status of local causation. So yeah, in some sense, it's more real in the micro level. You want to use more real as more fundamental or something like that. And the other thing I was going to say about it was, so yeah, our perspective on configuration space from three-dimensional space will be this projection. So it's giving an account of how things are in our world. Is the projection, is the sort of what we see from one dimension, three dimensions rather, of that particle will be its projection, mathematical projection into three-dimensional space. So because the whole configuration space is discrete, then the three-dimensional space has to be discrete as well. And it's the discretization that led to the motivation for the collapse came from discretization. You have to discretize both the magnitude of the wave function and the cells, in space, in order to get this configuration space.
Yeah, I mean, I think that's the bit I'm not quite getting. So I get that the configuration space is discretized, but you could project that I think, into a continuous space-time. Like I don't quite see why you would need to then discretize the physical space as well.
Oh well, I mean, if you want, I mean, the values will be discretized. They'll only have values at certain distance apart. So whether you say that's a discretized space or not, it's up to you.
I was thinking like a discrete geometry. That's what I mean by a discretized space. I thought that's what you meant by a discrete physical space. But maybe we're talking past each other.
I think, yeah, we're just thinking just of it like a lattice.
It is a lattice, so yeah, I think there's various ways you could do the discretization. I was thinking that the cell size might be proportional to the wavelength of the effort, because you need to change things more rapidly when the wavelength is shorter. So it wouldn't be a fixed background sort of discretization of the space. It would be more governed by the dynamics of the wave function itself. So the discretization sort of lives in the wave function, and it looks discretized when it's projected into space. But I guess, yeah, maybe you wouldn't say that's a discretized space. It's not a fixed one anyway.
Mm-hmm.
It's sort of variable with space and time and the particle that's involved, the size of the cell and so forth. Do you get the idea?
Yeah, I think so. Thanks.
Patrick?
This is kind of on that question, but maybe I've confused it slightly. But isn't the idea wouldn't the idea here be that if you had a continuous space, and then if you measured a normalized wave function in it, at any one specific point in that continuous space, it would have a negligible magnitude, because otherwise it wouldn't be normalized, right? Because there's a continuous infinite number of locations in the space. So it seems like you couldn't have a lower limit for, the magnitude of this wave function at any given point. Otherwise, it would be below that limit at every point in a continuous space, right? Or have I confused the question?
Couldn't hear very well.
Yeah, sorry.
Oh, sorry.
Yeah, volume was dropping in and out. So
Oh, right. Okay. Sorry. Yes, I'm glad that didn't happen during my own talk, but it does happen.
No.
The idea, I guess what I'm trying to say is if you're thinking about a continuous space, and then you've got a discrete, so a minimum value of the wave function at any given point, then surely that wouldn't be normalizable, because you've got sort of an infinite number of spatial points.
Oh, I see what you mean. Yes.
In any given area. And if there's a minimum magnitude, then you've got an infinite magnitude overall. It seems like you wouldn't be able to have a continuous space and a minimum magnitude of the wave function and normalizability. It seems like one of those things would have to go.
No, I mean, the minimum magnitude is not for each cell. Well, I mean, there is a minimum magnitude that can take on before it becomes zero. Not quite sure I understood.
No, I think the point here is that you'd be right. If the wave function had a minimum magnitude and it kept on spreading out, then it would be not normalizable. The point is that the wave functions then has to drop to zero, so it has to be finite in volume.
Yeah.
And that's what makes it not normalizable.
But it would also seem that the space that it's in would need to be discrete, right? Because if the space it was in was continuous, then within any given sort of volume, there is an infinite number of locations within that volume if the space is continuous. So that would be a reason why you need to have a discrete space, right? Just because you can't, you couldn't have an infinite number of locations, a continuous number of locations,
Yes.
and a discrete chance of it being any one.
Yeah, there's only one magnitude per cell.
Yeah, so you have to have these
That's right,
cells.
that's
You have to have it to be
So it
discrete.
is discretized in that sense. Yeah.
Yeah.
So the configuration space has to be discretized because we have
Yeah.
one magnitude per cell. Yeah.
I guess I had a sort of separate question, which is maybe you may not have much of an answer to this, but I suppose a question for this interpretation as well as for other ones is where the kind of requirement of normalizability comes from in the first place. Why couldn't you, if you've got these sort of wave functions and these are your sort of primitive things, why couldn't they just extend? Why do they have to get smaller as they get wider? And why is the area under the water than one? I don't know whether you would have any thoughts about this, or whether this is just a stipulation. You're just look, this is just part of our interpretation. There's waves and then normalizable. Because obviously, I think that is probably how a lot of other people would respond to that question. But I wonder if you've had any thoughts about it.
Well, I mean, if you made all the numbers very small, the size of the cell and the minimum magnitude, then no matter how much it's spread, it would never reach the minimum. That would work at least for a finite universe if you made the numbers small enough.
Yeah, so
But we're assuming that that's a bit ad hoc to keep making things smaller, just so the thing doesn't collapse. So, but it seems more natural that if you're having a discreteness, that it won't be just tailored to the universe so that nothing ever collapses. It's more, do you understand?
I think the question was about on the normalization of the wave function.
Oh, I see.
And why does it need to be normalized? Well, no, that's. I guess that's a good question. I don't really have an answer. I mean,
I do.
You and everyone else, maybe.
Good. Okay.
Because I mean, normalized to one because the probability Well,
I mean,
what's
that's the
not.
probability interpretation of the
I
wave
know,
function.
I know.
So yeah,
I know,
but,
but
as
to
a
be-
physical wave function.
Yeah, okay. But to get agreement with normal quantum, standard quantum mechanics, we need the wave function to be normalized.
Yeah, you need it to agree for sure. I guess the question is just where it comes from. But I mean, you're not the only people with that problem, right? Like a Bohmian who thinks there's a quantum potential. You can ask, well, why can't the quantum potential just be an infinite sine wave? Like, what's to stop it from being that? And they say, oh, well, it's, there's restrictions that we just stipulate, So obviously this is you're not the only people in this boat. But I guess I was just wondering whether you'd have any thoughts about like where that requirement comes from, other than just saying, well, we stipulate it because we're going to need to do that.
Yeah.
Well, I think, it's arbitrary in a sense, because we don't have a probability interpretation. What that magnitude is got no natural unit. So but we do have this a dimensionless number, which tells you the number of cells that are non-zero. So I guess, and if they get too great, then the overall, each per cell, it gets too weak. So I think there is an absolute thing going on there. The number of cells that are non-zero. And the actual, talking about it as normalized, yes, whereas to 1 is an arbitrary thing to match normal quantum way of doing it.
But it's not just to match the normal quantum thing, I don't think. It's that there's some.
Oh, John, you either have to turn your microphone on or come over.
Yeah. Okay, it's something like this, that there's only the particle can have a 1 quantum presence in this cell and a 1 quantum presence in that cell and a 2 quantum presence in this cell and so on, can't it?
Mm-hmm.
But it's got to have a finite sum.
That's right.
Yes.
And so thinking of Sam's question about projecting it onto a continuous space, you'd only be able to give the 1 quantum presence to 1 point and then 0 for a gap and then to 1 point and so on. So you would really be only projecting onto some of a countable number of the points in a continuous space, and the rest would be redundant. You're not really projecting it onto. But the normalizing is just that the sum's got to be finite. There's only so much of the particle to go around.
Yes.
And normalizing to 1 is arbitrary, but the particles can only have so many quanta of presence to distribute into all these cells. Isn't that the idea?
Yeah, I guess one could do the normalization in a different way, and you wouldn't need to normalize to 1. You just have to, your probability interpretation would be the total magnitude.
Yeah, remember that
the magnitude of this volume divided by the total number of cells that are occupied.
So you could say, because it's dimensionless magnitude number, you could say, there's, well, we had some estimates. I can't remember how many. 10 to the, how many, I can't remember now, 10 to the
36 or something, yeah. So it's quite large, this relative volume.
So, yeah,
Sure.
Yeah, 10 to the 36. So there is an absolute number for the number of.
Yeah, I guess you get a view where every electron has a certain number of quanta that it would have, and those are distributed among a certain number of locations, but there's a finite limit to them. And I guess you get an interesting question as to sort of why you can't have some waves that are bigger than others. I don't know. It's an interesting thing to think about.
Yeah, that's interesting. But,
All right. Well, maybe one last question.
Okay, thanks.
No, that's it. Okay.
I think we're out of time.
Yeah,
so
out of time,
we thank you for your questions.
Hello, good.
Yeah, and thanks.
And thank you for attending our session.
Yeah, and the four of you, it was a great session this morning.
Yes, I really enjoyed this.
Yeah, this morning.
Time.
Thank you all
Yes.
for coming to ours. That was great. Really good feedback. Thank you.
Thank you. Thanks for the session.
Yeah, thank you.
Thanks, folks.
Thank you.
Thanks.
Okay, so it's the plenary next. Is it Jacinta? Is that right?